Yeah, so I'm going to continue from where I left off last time. We're going to see the map from the evaporating black hole setup in the semi-classical gravity picture to the fundamental description as a non-isometric map and understand its consequences. So yes, let me write down our simple model for this holographic map again. So we said that the map is a map from the degrees of freedom in L in the interior of the black hole, which we said were the left movers, which were just some initial matter that was thrown into the black hole, and H small r, which referred to the right movers, which were the growing number of modes in the interior, which were entangled with outgoing radiation particles. Okay, and this, the holographic map takes us from this to the boundary description of the black hole, which we call HB. Okay, and at times after the page time, the dimension of LR is much bigger than the dimension of B. And so we model the holographic map as follows. We take L and R in the input, and then we act with some random unitary, some typical unitary drawn from the Haar measure. And then part of the output will be the system B, but the dimension is not large enough to account for the whole output. So in the rest, we say we have some system P, and we project out we project onto some state 0 in P. Okay. And we also add some overall factor of the dimension of P here, which will be needed to make certain things work nicely. Okay. Okay, and so overall, we know that in addition to this system, we also have the radiation system. So this was the map V. And then in addition to this, we also have the radiation on which the map acts as the identity. And also we can, in general, take some mixed state of L. So we can purify that state by adding some other reference system, capital L, which we'll also include in this picture, and we'll have the same dimension as small l. Okay, so overall, we have a map which looks like V from LR to B, tensored with the identity on capital L and capital R. Yeah, capital L is just some auxiliary system, which, so in general, I can have some mixed state rho L in my input. And now,
on the L side or LR side?
On the R side, I'm going to assume that I always have a pure state on small r and capital R together. So now to purify this remaining thing on small l, I'll include some auxiliary system which has the same dimension as small l. So then that just simplifies things because it allows me to consider just pure states in the input. Okay, so yeah, now U is a unitary because in the output I've projected onto something. In fact, I take U to be a typical unitary from UN.
So basically, is that you have a unitary acting on HR and tensor product HR, such that its action on V should become that non-isometric you started with. Is that correct?
So this is just my model for the non-isometry that I want. Yeah.
But I'm saying, who had is some fixed subspace of HV tensor product, whatever.
Oh, yeah. Sorry, this is badly written. So by this, I mean projecting onto some reference state, which I call 0 in the remaining system P.
Right?
Yeah.
So there's a God-given state 0.
Yeah. Yeah.
Regardless of L, R.
Yeah, exactly. Yeah.
And the idea is that this typical unitary, when you just restrict its action on B after taking into account the projection on the rest, gives this non-isometric nuance.
Yeah, exactly. Yeah.
It's every non-isometric map of this one.
Yeah, you can always write any non-isometric map as some unitary followed by a projection.
The assumption is that U is
Sorry?
the assumption is that U is typical.
Yeah, exactly. Yeah. And yeah. And sorry, I should have said any linear map can be written as unitary followed by projection.
That's what I was gonna ask. So non-isometry just mean a linear transformation.
Yeah. I should have said just a general. Mhm.
We're like completing a rectangular matrix into a square matrix by adding additional zeros.
Exactly.
One. And just to ask, sorry, although if I work with prime numbers.
Okay.
this May not have, this picture may not work. Right? If the input is 7-dimensional, the output B is 5-dimensional.
Uh-huh.
You can never write it like that.
Yeah. I'm assuming.
So what you said is probably not. There's been some. Because it's not a factor, right? It doesn't factor.
Yeah. Yeah, I guess in that case, I would need to have some Hilbert space which has dimension 7 divided by 5, which. Yeah, I'm not sure, but
Yeah.
I think under some assumptions, it is true that you can write every.
Large.
Yeah.
Probably, yeah.
Yeah.
So I mean, this as a mathematical statement, when you use this as a shift.
Mm,
It's fine. I mean,
Yeah,
that's it.
yeah. yeah.
Right. And you work with the team on-
I'm projecting onto some arbitrary state 0. Yeah. What the state is will not be important in any of the things that we do. Although, we also have a dynamical version of this model which I probably won't have time to talk about today, but in that you find that there is a natural state to choose for the projection, and it has some specific form. But for this simple model, so I should say this model is just for a single spatial slice like I drew last time, or a single space like slice. And then as you evolve to different space like slices, you can do that in this model by just changing the dimensions of the systems. But this is not explicitly into a bulk time evolution or the boundary time evolution. It's just for one time.
It's like you know, some, but in the old days, which are really old, we used to think that the only way the information puzzle can possibly be resolved is if what's called bleaching occurs. Namely, how can it be on a nice slice that the Encyclopedia Britannica is inside while the information has come back out? Okay, and the only way it can happen is there's some mysterious process, so that it doesn't matter whether you threw in the Encyclopedia Britannica or, to be politically correct, the Ramayana, they both become this unique state, okay, bleached out of content, and then it's okay. And is this sort of implementing that idea a little bit in that, what you can project into the black hole you project in, and the rest is some, state regardless of what you project. It might be a vague question, but it sort of smells a bit like that. Yeah, final, yeah. There's some final state.
Yeah, it looks a little bit like that, but in this case, note that this is not a final state projection, because here, like from that picture that I drew last time, nothing special, like the projection is not happening at the singularity or anything like that. It's just the projection is in the map from this to this picture of the black hole, and so in our setup we kind of separate what happens in the bulk picture and the boundary picture. So here we would say that in the bulk picture, the Encyclopedia Britannica or the Ramayana is inside the black hole. The information doesn't come out in the radiation. But once you map from this picture to the fundamental picture, if you're at a time after the page time, then the information is actually contained in the radiation.
But I mean,
and it's not in the black hole in this case.
I mean, in the bulk, you just repeat what you said, sir.
Yeah. So this is just saying that in the semi-classical picture, you will have information loss. Then, but in going from the semi-classical picture to the fundamental picture, because of this non-isometric map, you end up sending the information from the black hole into the radiation.
But the fundamental picture is the correct one, right? The
Yeah.
semi-classical approximation.
Yeah, exactly.
I'm saying in the fundamental picture, you project, it seems like you have a huge number of states in the semi-classical approximation.
Yeah.
But you only have a black hole world. And try to construct that much bigger inverse space. What's really happening is you're projecting into some unique state times the black hole.
Yeah. Yeah. Yeah.
Okay, thank you.
Shreya, just,
Yep.
Little L and little R,
Mhm.
what are they really? I mean,
Yeah, so sorry, little L was some infalling matter. So it's some relatively small number of degrees of freedom. And little r is the growing number of degrees of freedom, which are all entangled with the outgoing radiation, which is capital R.
and I can make a distinction between little L and little. I mean, the little L is like the infalling matter. So the
Yeah.
matter is still infalling. Something.
Yeah. Yeah, but it's relatively small compared to little r.
Does it play an essential role?
No, little L is not really important. It's just included to make the model a little bit more realistic. And actually in the version that, like, I should in principle also include some additional system called F, which can take into account other degrees of freedom, like degrees of freedom which are outside, outside the horizon. Sorry, I didn't. So sorry, the little r's were all inside the black hole. And then in principle, I could have had some other degrees of freedom which were outside the black hole. Or I could have had some UV degrees of freedom, and all of those things I say are in some fixed state because they're not really important for our discussion of what is happening in the black hole interior. So adding such a system in a fixed state in the input doesn't change anything about the calculations. So for simplicity, I'm just going to remove it. But yeah, you can include it.
The fact that the actual number of states is so much smaller, only a black holes work, whereas if you were inside, you're such a large volume and you're in low curvature, and you might have thought you should have many more states. This is okay. Is it? I mean, I could be inside a black hole right now, and I would say I have a volume's worth of states. But if I were inside a black hole, I'd be seriously.
Yeah.
And I mean, this is the key question, right? I mean, why am I serious?
Yeah, that's part of what I wanted to talk about today.
Okay.
Yeah.
I remember the notation. B was the state of the boundary.
Yeah, B is the boundary description of the black hole.
Yes. Okay, good.
Capital B, yeah.
Zero was what is it?
0 is some arbitrary fixed state in the remaining system P if you want the map from LR to be a unitary, just to match the dimensions on both sides.
Sorry, and R was radiation. Capital R was radiation.
Capital R is radiation.
Little R was.
Little r is the right moving modes inside the horizon.
The hockey part.
Yeah. Yeah.
And little L was something.
Little L is just some infalling matter, which is some small number of degrees of freedom.
And what was F? Little F?
Yeah, little f was just something I added now. It's not important, but it could be some degrees of freedom outside the horizon, or some UV degrees of freedom that we choose to freeze and put in some fixed state.
And 0 was at one state in a big system P.
0 is one state in the system P.
And P was.
And P is, yeah, P is chosen to be some arbitrary system such that you can match the dimensions on both sides. So if you include F, then you want the condition that this is true.
Okay, go that condition is satisfied at all times. We need to keep changing these multiplications.
Yeah, P is not fixed because you want to keep increasing the size of L and R and decreasing the size of B. So the size of P will change according to that.
And 0 is an arbitrarily chosen state.
0 is arbitrarily chosen.
Little f is the purifier, or it's something.
No. Yeah, let me just remove little f because it's going to cause, it's just something that I chose to put in a fixed state. Yeah, actually, let me not remove it, but it's just some additional system inside in the input, which is in a fixed state, and it can take into account degrees of freedom outside the horizon, which in principle I should include.
Like radiation. Degree of freedom outside. Oh, inside the system, but outside.
Yeah, inside the gravitational system, but outside the horizon, which will be much smaller than L and R, so it's not as important as.
It's not gonna play anything.
It won't play any, like, yeah, the equations are the same whether I include it. I guess including this lets me also consider the case where LR can be smaller than B. And then I can include the case, in that case, this map will be an approximate isometry. So it allows me to discuss times before the page time.
What property of U is very important? I mean, I know you want to, for convenience, because they will be taking typical in the R ensemble, but could I have taken some other ensemble which is less complex, or what property of U is the thing that's relevant?
We end up using the measure concentration on the Haar ensemble. So this is why we took it to be of this form, and
So if U was a very low complexity operator, would some of the
yeah, so recently there was a, like, you can also assume that U is pseudo-random, which we didn't do in our, it was a recent paper by Preskill and Kim, where they to a case where U is pseudo-random and then it still works. Yeah.
Just repeat.
Well, actually, no, they didn't show that the measure concentration stuff works in that case.
What property of freedom? Okay, but for mere models, what is measure? Does this say what is the?
Oh, that's something that I'm going to talk about in a lot of detail today.
Okay.
But
Pseudo random, if you can once define, if you don't mind, what those terms mean then. Okay, as you go along.
yeah. Okay. So okay, so the statement that I want to show today is that even though this map is highly non-isometric, which means that in general, it will not preserve inner products between states, and it will send some states of norm 1 to 0 to just 0. So they don't exist in the fundamental picture. I want to show that for states with complexity which is smaller, which is sub-exponential in the black hole entropy. The inner products are preserved. Or they're approximately preserved. And the errors are also of order exponentially small in the black hole entropy. Okay, so then that, like, the overall upshot of that will be that the additional restriction that I should have had in addition to low curvature and low energy density is that the complexity of the states that I consider should not have been exponentially large in the black hole entropy. Yeah, I'm going to define that more in just a minute.
Sorry, okay, it might seem, as we were just discussing in this large volume, you can have so many states, but actually the number you can build out of collapse will last. And so for them, the ones you can actually build, you're not going to see any big violation of locality. It will be approximate the fact that what look like orthogonal states are. Is that?
That's the idea, yeah. Or like whatever you can imagine a reasonable observer inside the interior could do while they're inside the black hole, that could only produce states which are not so complex. Yeah.
I mean, I'm just saying, in a sense, naively, you might have thought, look, if you can have other states, then you might have to begin with being in one of those other states. You know,
Mhm.
and then, you know, this whole thing goes wrong. The inner products are not approximately preserved, et cetera, et cetera. But perhaps consistent with your pictures of is the thinking that you can't produce the states. It might seem like you have these bags of gold possible inside, but you can never produce those states starting from any nice collapse. So
Yeah, that could be one way of
and
thinking
it'll
about it.
all- Something like
Yeah.
You said that time evolution doesn't produce very complex bulk states, is that effect the singularity is finite?
But even for, like, I think if you perturb these Hawking modes in any way, you would get a singularity in the past at some point, right? Like, so I'm not sure that is the reason why.
Why time evolve with the bulk and produce arbitrarily complex states?
Yeah, I think that everything that we say will break down at times which are exponentially large in the yeah, yeah. That will also come out of the calculation that I'll show.
Sorry, to show you that, but this map, it's just a map between Hilbert spaces. It makes no reference to the particular state, particular entangled states the system happens to be in, or does it?
Yeah, so far we're allowing any input state, so it doesn't have to be Hawking state or anything. Yeah.
So the fact that the Hawking radiation and the inside is highly entangled, that is not going to go into.
That is not going to play a role in this discussion. Yeah. Okay, great. So, so before we show this statement, let's first at least understand what happens if you compute averages over this random unitary group. So the first statement that we'll show is that if you look at, yeah, okay, so I'll call this state, so I'll consider an arbitrary state. Okay, and I call the states here psi, and then they map to some corresponding states psi tilde. Okay, so the first thing I'll show is that for any psi and psi 1 and psi 2, which are chosen independently of u, the inner product before and after applying the map is on average the same. So if I compute the average of this quantity, which will involve computing and then there'll be some overall factor of p. Okay, then this will just turn out to be, once I use the average of u times u dagger, this will just give me psi 1, psi 2 overlap.
Not including the F now.
Yeah, I just removed f for simplicity, but it would be the same if I had included it.
Then there will be tensor product HF, and then you still go to HP tensor product.
Yeah, no, I'm fixing the state on f, so so I don't have any non-trivial input. Yeah.
But F is the Hawking point outside the black, like the horizon, outside the horizon, right?
No, that is r. So
Okay, that's, I thought.
R is something in the path.
I thought the distinction is that the vertical line was the boundary. If you're doing JT coupled to gravity, that was the boundary of where the gravitational system ended.
mhm,
That 45-degree line inside was the black hole horizon.
mhm.
And then I thought little f was supposed to keep track of quanta between 45-degree line and vertical. So that it's outside the horizon,
Mhm.
but in the gravitation, as opposed to capital R, which is
totally outside of that.
Is that correct?
Yeah, but somehow the modes that you got in capital R are the partners of the
Yes,
things which
yes.
are inside the
They are
horizon.
supposed, oh, they are, they've already come.
Yeah, they've already come out.
They come out.
Yeah.
So I agree, that sounds reasonable. So just wondering, going back to Shiraz's question, that sort of the particular state that Hawking tells us is actually a statement about entanglement between little f quanta and, L quanta. R quanta.
Capital.
Well, okay, that's true. Okay, maybe.
Yeah, I think we can just ignore it.
Maybe F is- okay,
Yeah,
fine.
yeah, F is just some,
Most
yeah,
of the stuff came.
yeah, yeah. Yeah, so the Hawking statement would be about entanglement between small r and capital R.
And capital. Okay, fine, fair enough.
Yeah.
In that map, capital L also is a spectator.
Capital L is also a spectator, yeah. So you just act with the identity on that. Yeah. Because it was just some reference system. Yeah. Okay.
So where on the right hand side, you don't explicitly write HL.
Yeah, I should. Sorry, that's just a
P or-
no. That's a mistake. I should have written.
Yeah, that's because it's auxiliary on both sides.
Yeah. That's right.
So, Shreya, in the other system, auxiliary system that you value is P, is much bigger
P. Yeah.
than. I'm trying to understand your result.
Yeah.
So most of the time, for most of the unitaries, a lot of your state would then be in the auxiliary system.
Which gets
And then
killed. Yeah.
you lose a lot by projecting.
Yeah.
So it sounds like you need to make some assumption for this to be true, or am I wrong?
No, this is just true.
Okay.
So,
Average-
yeah. Yeah, I mean, part of the reason I've also added a factor of P in my map, which was partly to compensate for, yeah, but your intuition is right that you project out a lot of your Hilbert space, but still it's true that, yeah, so note that one assumption that we made about these states in this calculation was that they don't depend on U, because when we did the average over U, we just included these unitaries, which we've written explicitly. But if you actually wanted to find the null states of this map, then it seems reasonable that they would depend on U. But in any case, so this is what the average result tells you, but we shouldn't be happy with just computing the average, because we said that, we're not defining the map with an average. We're defining the map with some typical U. So at least we should compute the fluctuations around this average.
Sorry,
Yeah.
Just understand. If you don't mind.
Yeah.
What is that?
Sorry,
What is what
mod.
dimension of?
Oh, yeah. So, yeah.
So the average of this guy. Why is there a mod being there?
Because because this factor of square root of P was in my definition.
So you're multiplying by unitary and rescaling by.
Yeah.
By mod.
That's sufficient. I should also say, let's say, take the extreme case where D is nothing basically and everything is P.
Yeah.
Then you should just lose everything, right?
Yeah. Surprisingly, according to this average, you don't. Yeah, it's very counterintuitive somehow.
No, but I think what will happen is that on the average, you'll get 1/p of it when you project. Right, some random state in that other guy. So the amplitude of on any one guy is like 1 by square root P. So you mod square that gives you 1 by P and this 1 by that P complex.
Okay, so I think Shiraz saying it makes sense, but why is it not P and not P?
Because sorry, this has, I added 2 factors of, because I added, sorry, do you mean just at the level of the calculation, or do you mean?
There, I meant from square or and I was thinking that on an average, the probability would have.
Probability will be 1 by P, therefore amplitude will be 1 by P.
So then why is there a?
But that's the inner product.
Yeah, so if you had,
Oh, each of them will be a fraction. Okay.
Yeah. Yeah.
Okay, I understand. Yes, okay, thank you.
Okay, and now what's confusing me, Shreya, I'm sorry.
No, that's good.
Now what's confusing me is now suppose we take the other limit. Where the auxiliary system is much smaller than.
Okay,
In that limit, almost none of it goes there.
Yeah.
So then it sounds like an overkill to multiply by K.
But in that case, P is very small, so you're just multiplying by some small number to compensate, right?
But P is a ratio? I thought P was the size of the data.
Yeah, yeah.
So let's say
Oh.
that B is a billion and P is a million.
Mhm.
It sounds like an overkill to multiply by 1,000. Because almost none of your state is there. So that's a sort of small fraction of the whole thing.
It's the dimension of the input state onto which you're presenting.
Yes.
So if you're not presenting the dimension of one, then
If you're not, no, so I was thinking, maybe I'm thinking wrong, I'm probably thinking wrong. But I was thinking that if P is very small compared to B, then almost none of it goes into P, but that's not how I should think, because it's a product. I see, you say that there is always some part that's in P. Yeah, that's okay, sorry, you're right, thank you, Rachel, thank you. Yeah, the way to think is that it's a product, so there's always a part of the state in P, it's not like a sum, so you're rotating it.
Yeah, that's right. Yeah.
So then in P, there is a part of the unitary. So there's 1 by square root P level. Right. Okay, thank you.
One more question. Are these states the states with complexity less than exponential?
So far, no. But note that I'm computing an average. So on average, later I want to make a statement about typical U and say that with high probability, this will be true for the set of states of low complexity. So far, I have shown you very little because I've just computed the average over U. And I haven't even found the fluctuations around this average yet. So yeah, so this would be, yeah, if this were exactly true, then that would be very strange because this seems to be saying there is not even some small error, but at least there should be some error in how well this works, which we can see by computing the fluctuations. So the next thing we can try to calculate.
Sorry, Shreya, so
Yeah.
this 0P, the
Yeah.
choice of that particular state is irrelevant.
Yeah, it turns out to be irrelevant.
Because you can rotate. Because I absorb that into absorb that into the U.
Yeah, exactly.
Good. Yes.
I should answer that in some the fluctuation in the inner product should be 1 over. Or 1 over.
No, it actually turns out to be suppressed in the size of B. Mhm, mhm. Yeah, so yeah, so that's the next natural thing to try to compute. Yeah. Sorry. Okay, so we can try to compute this difference. Okay, and I won't write out the whole calculation, but this will, because it involves this thing squared, it will involve, instead of the average over U times U dagger, it'll involve the average over U times U dagger times squared, basically. And we wrote out expressions for how to compute these things in the first lecture indirectly because this involves some sum over permutations, similar to what I wrote the context of the equilibrium approximation. So anyway, so you can compute this. And when you do, then you find that this is essentially 1 over B. So this is saying that if the size of B is large, then if I take some arbitrary psi1 and psi2, which are chosen independently of U, then for any such pair, I'll find that the inner product is preserved. Sorry? Yeah.
And size of P makes no difference.
No, it somehow cancels out. And,
Oh, P is much bigger than it. I mean, it's less of a approximate.
yeah, this might be assuming that P is smaller than B, actually.
Yes, one.
Will be much bigger by, yeah, given.
Yeah,
This makes sense, yeah.
yeah, because I think when you do this average, you get, yeah, I think the expression had factors of both P and B in it, and then eventually, yeah, in canceling out P, it probably was assumed that B is bigger than P.
But sort of realistically speaking, if you are modeling the black hole, as we were saying, you have a large volume. Even I don't know if it grows even more, but that the comment becomes more pertinent. But anyway, you have a large volume, so you might think that P is actually in dimensionality bigger than B.
Yeah, actually, just after the page.
Yeah.
Uh,
Isn't that, I mean, naively, that's the conflict with locality. Area versus.
yeah, maybe this is something that I can go back and check later. Not 100% sure. I think it definitely assumes that P and B together are large. I don't know if you have to assume that. Yeah, I don't know. I don't remember whether you have to assume that P is
Suppose P
smaller
is
than
one,
B. Okay.
then all the rotations happening in the other space.
Mhm, mhm.
Surely there's some separation cycle. It seems, but you're saying. But maybe.
Yeah, so if B is small, and this is saying that, I think that seems usual. If B is small, then it's saying that there is a large error in the inner product, right?
Larger.
Or like, yeah. And I think that makes sense because in that case, because you're preserving a very small part of your Hilbert space, you should have a large error. Yeah. Yeah, so I can check this, but actually, I think probably you have to assume that the whole dimension is large, but not anything about the relative size. Because just after the page time, I should actually have that P is
Yeah, just after the page time, P would be much smaller than.
mhm. Yeah. Sorry.
Suppose that that Hilbert space, suppose dimension of HR and HR, that product was equal to. You know, that auxiliary was nothing. Then this would have been completely trivial.
Then it would just be a unitary map.
Then there should be no suppression. I mean, you would have done exactly the same. So the fact that you're getting 1/B versus 1/B is what's spring from. But
Why you get 1/B at all?
Yeah.
Yeah. No, I mean, 1/B would have been.
So, well, let's assume the NP are some big numbers, but you know, it's much smaller than something. Bit string.
Yeah, and in the case where P is just absent, you could get the exact quality.
Yeah.
In a case where I think this is assuming the existence of P.
Yeah, and maybe taking both ways, but one bigger, something like that.
And it's assuming that both are big, but I think, yeah, I think when both are big, then things cancel out such that you're only left with 1/B. And I don't remember what happens in the, like how it correctly produces the limit where P is 1, but yeah, but the answer that you get is this, that this looks like it's exponentially suppressed in the black hole entropy.
You didn't assume anything about the straight side, right?
I assumed only that it's independent of U, because otherwise I couldn't have computed the average independent, like I would have had to take into account the U dependence of psi.
Yes. But that's natural, the input should not depend on the management.
Yeah, but I guess.
Related to that statement there, so is that the statement that the psi has less complexity, or that will come later?
Yeah, okay. So the key thing, so the reason that I haven't shown you anything like this statement yet is that from the fluctuations being small, I know that if I take a particular pair of psi1 and psi2, then with high probability, the change in the inner product will be small. But it doesn't tell me about if I simultaneously take a large set of states, with the probability that each of them deviates by a small amount still be high. So for that, I need to take into account complexity. Yeah, sorry. So I guess is the statement about the fluctuations clear? Yeah. Okay.
From your first lecture, for example,
Mhm.
do I assume that psi1 and psi2 are sufficiently formalizing with respect to you and
No. No, I don't need to assume anything about psi1 and psi2. Yeah. Yeah, but the reason why this is still not a very strong statement is that it's just telling me that if I take one pair psi1 and psi2, then with high probability, this change in the inner product will be small. But it doesn't tell me like if I take all of them together, will the change in the inner product still be small?
But I understand that this was derived by averaging over today.
Yeah.
So if I didn't want to do that, suppose I wanted to use the technology from your first lecture,
Yeah.
then would I be able to derive the same formula if I assume that psi1 and psi2 are sufficiently formalized?
Not quite, like somehow the whole context of this discussion is different because here U is not a time evolution operator. So
Correctly, U is whatever is the operator to generate your normals. But you're saying it could have been. So that's a generic.
yeah, but in this context, the interpretation of it is not at all time evolution. So yeah, so I'm not sure that it would make sense to make an assumption like that.
So it's gambling. Maybe it's different, but you say that you haven't yet shown this for many states, just for
Mhm.
the states.
Mhm.
But why can't you just pairwise apply this argument?
Because if I pairwise apply this argument, then I would get so this is essentially telling me that the probability of deviation of this quantity from 0 is small for one pair, but then if I have many, then I have to apply a union states in a Hilbert, the total number of states in a Hilbert space of dimension LR will be doubly exponential in LR.
Can I think of that with that the typical U that works for this case,
Mhm.
that may be different for this cases.
Yes, exactly. But now I want to show for a single choice of U that I can have simultaneously, I can have this deviation be small.
So
Yeah.
could I try an intuitive explanation of your one?
Yeah.
So suppose A labels an eigenbasis for B.
Okay.
A running from 1 to B,
Okay.
and I labels an eigenbasis for P.
Mhm.
So now you perform your unitary and you get some psi A times I. Sorry, some psi, forget the eigenbasis for A. You get some psi I times I, where psi I lies in B.
Uh-huh.
And I is the eigenbasis of P.
Okay.
Now we choose 0 to be one of eigenbases.
Mhm.
Okay, so if you computed the whole norm, it would be sort of psi I, and then some over I.
Mhm.
Right? And now you're computing only the norm now in what you're doing, and that would have been 1.
Mhm. Mhm.
Okay, now in what you're doing, you're only computing psi 0.
Yeah.
Okay, so that first explains the factor of P, because there were P such terms, and you're taking only one of them, so that's why you need to multiply by P.
Mhm. Mhm.
But now it also tells you that the averaging you're doing
Yeah.
is averaging over these inner products, which are in this large space of dimension.
Uh-huh.
So suddenly law of large numbers, it's a question of how well one inner product approximates the actual thing.
Mhm.
And since the deviations for this one inner product, because the size of this one inner product is B, that by the law of large numbers would be.
I see. Yeah. Yeah, you're saying that this inner product is being computed in a Hilbert space of dimension B.
Yes.
Yeah.
So how well does that one draw approximate the average?
Mhm.
Which we know is one. Well, the errors will be of order.
I didn't get it, sorry. One draw, what was the one draw?
Is psi I psi.
Is psi.
Psi zero is one particular vector, one. Okay, and actually it's psi zero plus psi one plus psi two up to psi p psi. Psi p minus one psi. Yes. Okay, that whole thing is one. But now you take it in. All of these are sort of random. So this is one draw of size B, which is going to have average 1 by P, and its fluctuations will be determined by the size of B.
So if all each of these inner products, size 0, size 2, size 2,
Yes.
as random numbers,
Yes,
right? Then that I understand this average will be kind of thing.
yes.
But if it is random, then the first guy will approximate the whole sum, would have to do with the factor of 1 over P, right?
Yeah, and she's got that.
No, I mean standard deviation.
Yeah, I mean, the standard deviation, why are you going that way? That's the part that.
No, so this thing is one is approximately 1 by P is 1. So we multiply by P. By P, so we're getting up. It's mean is 1, and the standard deviation will be determined by P.
They're not expecting all of it to be.
No,
We just want it's P times that to approximate.
to approximate it, right?
So that's that will be.
That feels like B, right? You just rescale the whole thing by P, and now the standard deviation is still set by B.
What about the fact that in silence, you should go on?
Mm.
In silence, you would have had in Shiva's language, psi 0 plus, sorry, the silent. Inside, you'd have had the various components.
Yeah, all of
the
them.
T components. That would have entered in psi 1, psi 2, because that's the exact answer.
Okay, the ones and twos are getting confused. She has 1 and 2, which is the actual state, mine were the basis.
No, in her actually.
Yeah,
So-
no, I think I can write down what you're saying. So no, I think saying something like this. So you're saying that psi tilde B is like, you can say it's like 1 over square root of B times some random phase. Something like this, right?
Each of my psi i's will be something.
Each of your psi i's or something like this. So yeah, so it has some,
Yes, and there will be 1 by square root 3.
And in each of those you have a fluctuation.
In each of them you have a
And
fluctuation.
psi 1, psi 2 has all of those peaks. In her psi 1, psi 2, it's the exact number. It has all of those peaks, and yet in the final answer, the final you get all of those peaks.
But psi 1, psi 2 was just 1. So there was no random variable. It's only psi tilde 1, psi tilde 2, which has some randomness.
yeah. So I think, is this roughly what you're saying, that you produce some random vector? Like by doing this, once you adjust for this factor of square root of P, you produce some random vector, like something which has random phases. But the number of these random phases is B and not
Yeah.
P.
Yeah.
And so that's why you get something which is exponentially
Yeah.
small in B. Yeah, I think that's right. Yeah. So maybe I should have said this to provide some intuition. We did mention something like this in our paper. Okay. Okay, so now, so like I said, so showing this for one pair of states, showing that this probability is high, is not yet good enough for us, because even if we had, so far we don't, so something like this roughly shows us that if you tried to write down a distribution, then you would say that the probability is exponentially small in B. But essentially the number of states in the whole Hilbert space is extremely large. So if you have a Hilbert space of dimension LR, and LR is bigger than B, then the number of states in it, so not a basis for it, but the actual number of states is something which is exponentially large, double exponentially large in the, sorry, it's exponentially large in the dimension of Hilbert space. So I need to Okay, so instead I'm going to show the following statement that with high probability,
I didn't understand last you said, because it's important.
it's probably not so important. I think I also got confused while saying it, so yeah. So let me write down something which is actually going to be useful. So we want to show that this thing is small for any pair psi1, psi2. From the set of states which I'll call S sub X, which would be some subset of the whole Hilbert space. Whose complexity okay, so I'll do this in a few steps. The first step will be to actually define what I mean by complexity here.
So now what are we doing here? I feel that 1/b are enough.
Yeah.
So here you're saying now there are special states for any pair from some set.
Mm-hmm.
What will happen that that case.
Yeah, so there'll be a very
Multiplying, so they got special about this set. That mod of that guy. So the average was the same as psi1, psi2 after multiplying by 2. And then here, so
Yeah,
what's
so-
special?
So the special thing here is that it only allowed me to show pairwise that there'll be a high probability
Okay,
of these things being closed, but now I want to show that for any pair in some set, I can simultaneously have this deviation be small.
Yeah, that's fine. Why does that, even if I had some states where the deviation is small, I could consider very large superpositions of the states and make the error large.
That will actually still be true, because the set of states of low complexity, which I'll define right now, is not a subspace. So you can always take superpositions of it and make the whole Hilbert space. Yeah, the worry was that maybe you can't have a single unitary U for which you can ensure that the inner product is small for all of them.
there's nothing special about psi1 and psi2 for which you established that result. Right?
Yeah.
U was I thought, some kind of generic unitary, not in any way tied to the particular state, psi1 and psi2.
Mhm.
You're considering that.
That's true. That's true. But this is a statement about averages. If I wanted to make a statement about some typical U and deduce it from this standard deviation, then it's not true that I can simultaneously. So this would be true for one set of states for a large set of U's. And then it would also be true for another pair of states for a large set of U's. But if any of these, then it's not clear if the overlap of all of those sets will still have a number of U's.
And that's why in your set, you will not choose too many.
Yeah, we'll yeah. So that's why what we'll show is that the number of states with this restriction on complexity is sufficiently small that we can have the statement be true for all of them using the union bound.
Statement is that there exists a unitary
Mhm.
which reserves the inner products approximately for those numbers.
Not just that there exists, but with very high probability, you can find like if you draw some unitary from the higher ensemble, then there's a very high probability that it'll satisfy this for all of those states.
That set may change depending on which unitary you pick, but there you can, there always exists.
Yeah, but most unitaries will still be contained in the overlap of all of those sets. Yeah.
And this is like a mathematical statement that you just takes that 1/b and puts it in the exponent.
Yes, exactly. That's a set of results that are called concentration of measure. And that's, yeah, but that's right. Exactly. Like, so this was a statement about standard deviations, but we'll have a statement about probabilities of deviation. And we'll say that this is essentially exponentially suppressed in some power of b. But that's exactly right.
That's why you get with the dimensions of the figure itself.
Mhm.
Deviation is significantly larger than 1.
Say it again, sorry.
The probability of your deviation being much.
Yeah,
larger
yeah,
than 1.
exactly. Yeah, I should have written it. Mhm.
I understand that you want to make a restriction on the total number of such pairs.
Yeah.
But why does it come from an upper bound on complexity?
That is, we'll show that putting an upper bound on complexity is a natural way of deriving a restriction on such a number. But in principle, the only thing that I'll use in the end is the number of such states. At least in this argument based on the random unitary. Yeah, so there are some limitations of this argument. But the point is to show that restricting complexity does give you a sufficiently small set.
This relatively geometric results that if you on a sphere in the dimension,
Mhm.
you want to find vectors that are approximately orthogonal,
Mhm.
then those go like each dimension.
You mean the probability of that goes like or
No.
sorry.
Yes, if you want to find a set of vectors in some d-dimensional space, which are approximately orthogonal,
Mhm.
then those go like e to the, I mean, let's say the approximation parameter is some alpha that figures in the exponent, but at the end of the day, it will go like e to the alpha.
Yeah, so the number of orthogonal vectors is much larger than you expect.
Yeah.
Yeah, that's right. Yeah, I think.
How related to that?
Yeah, I think that intuition is consistent with like just being able to fit much more into your Hilbert space than you would expect if you allow approximate orthogonality instead of exact orthogonality. Yeah.
But is that the only content of this, or there's some?
That is, yeah. I don't know if you can like derive this from that statement, but
Yeah, sorry.
I think it's very related to this. Yeah. Yeah, I mean, this is why writing down that ansatz for the vector in B with the random spaces also gave you the same answer. Like it showed you. Well, actually, though that was a smaller set because that was just. Yeah. Anyway, I think what you said is related to this.
You can pull the boards up and down.
Oh,
By pressing the bar. So there's some bar here.
oh, okay. Great.
All the books.
Okay, nice.
Press the wrong part of it.
Oops.
No.
It doesn't go further. Okay.
You
Yeah.
have to put it more up.
No, this is good. Thank you.
Use the board.
Okay, so now let's define what we mean by complexity. So to define this, we're going to model the whole system L, R, capital R, as a system of n qubits. Each with some dimension q. And
I somehow forgot what capital L.
capital L was the reference system which was used to purify small l.
Feedback.
No, it has dimension, same dimension as small l.
Purifies that smaller. And this was used somewhere before.
It's not important, yeah. Yeah, so, okay, so we can imagine starting with some reference state here, which we could take to be anything. We could take it to be something like Hawking state, or we could take it to be some state 0 of all the qubits, but it's something which is not very hard to construct intuitively. Okay, so if you have some computer, then this could be like the natural computational basis, something. Okay, and then, so one thing that's true is that we can find some set G of 1 or 2 qubit gates of some order 1 number, G of 2 qubit gates. Such that any state in your Hilbert space can be constructed by acting with such G's on all possible pairs of qubits. Okay, so any psi in this Hilbert space can be constructed as yeah. No, yeah. Okay, so this means that I consider all possible pairings like this, and so on between all possible qubits. And then if I have sufficiently many of these, then I can get to all the states in my Hilbert space. So then I can define the complexity of any given state psi as the minimum number
and capital L was the purifier, right?
Yeah.
Capital L purifier.
Yeah.
And the outside radiation together as a system of qubits.
Yeah, because the most general bulk state that we considered lives in that system. So yeah, so we just consider the whole system. So we find the complexity as the minimum number of gates needed to construct the state psi. It's just true that you can choose some order 1 number of gates. So this is a result from quantum information that it's possible to choose some order 1 number of gates. But so the number of the set that you choose from has an order 1 number of gates, but but then you apply any number of them in this circuit. Yeah, that will have to be very large for generic states in the Hilbert space.
But that's not if I only got an order 1 number of gates. I'm only touching it.
Sorry, the set of 2 qubit gates that I'm choosing from is order 1, is some order 1 number. That's just because 2 qubits have an order 1 number of things that I can act on them with in any case. But then in constructing my circuit, I can act with these gates on anything, any number of times.
Oh, I see. I act on any 2 bits.
Any 2, yeah, I can act on any 2 and I can repeatedly act on them and so on. Yeah, yeah. So the number of gates appearing in the circuit will definitely not be order 1.
G doesn't depend very sensitively on the set that you start with.
Yeah, this you can make various choices for this, and I think the choice is not unique. The only thing that we'll use about the set of gates is that there's some small finite number, like some order 1 number of them.
So I can choose an order 1 number of 4x4 unitary matrices.
Yeah.
And then apply them on any bit section.
Exactly. Yeah. Okay. And then I say that the complexity is the minimum number of gates in this circuit needed to construct psi.
Sorry, if you are moving from qubits dimension to
Oh, yeah,
And I just want to know, is there?
no, I just,
Or do you want to?
no, it doesn't.
With that, but the final notion of complexity will be independent of dimensionality. Just to.
Yeah, somehow we'll do some counting of like the numbers that we actually have to keep track of will be much larger than any numbers that, like, it doesn't matter whether this Q is 2 or not. Yeah, so I should just have said qubit.
Yeah.
This complexity, basically, how much of the system is affected? Is that what you want to measure with this? What is the spread of the status?
Yeah, in general, complexity can be thought of as a measure of the spread. So there are many different measures. This is what is called the gate complexity. There are some other measures which are more directly connected to the spread. But yeah, but this is the definition that we'll be using.
But then that would be useful if, let's say, for some small number of qubits or qubits, let's say 4 qubits or 5 qubits.
Uh-huh.
This G is bounded. Is it bounded? This gate number of gates required to achieve any given state.
Yeah, sorry, I think that I just wrote this badly somehow. So G is the number of gates that I'm selecting from.
Oh, I see. Then let me not.
Thank you.
Let me call this like if this circuit is, huh?
The number of gates required to
Yeah.
achieve, I give you a state for 5 qubits. And then the number of gates required for that, would it be bounded? Because what I'm saying, in just a small system, can there be states with arbitrary eigenvectors? If so, then this particular thing that one wants to measure how far it is spread out is a little suspect, right? Because you could have complex states even within small systems.
Yeah, usually you also define it with some error. And then I think it should be bounded, but I don't remember the results on that. Yeah, that's it.
Dimension of the Hilbert space or into the power.
Yeah, into the, so the complexity saturates, complexity is supposed to saturate at the depth. Roughly, most states in the Hilbert space will be complexity. Or circuit that.
Sorry, I was thinking that if I've got 10 states, I'll be on a sphere of sort of dimension 10. So I was thinking to go exponentially inside.
That's the total number of states that we think of.
Right.
Yeah, but here,
Complexity is still.
Complexity is also exponential.
Yes.
Yes. Okay, thank you. Thanks.
Say again, sorry.
So volume rho is like e to the power. When you apply n of these gates,
Yes.
you access a volume that grows like e to the power. So e to the power n should reach that e to the power dimension. So n should.
So N is the number of qubits in what you're saying.
Number of times.
Okay.
Number of times you're acting.
So if you add the number of times n with n of these gates, you say, what was into the n? The total
It's sort of
connectedness, the total connectedness, is it?
the total volume you're going to reach in the space.
Or in the sense, if you're going to start entangling or whatever, then each time you entangle two, so it's exponential. Like that. Okay, yes. And then that should become a generic state. And a generic state is the dimensionality. Yes. Okay, I'm with you guys. So it should be. Yeah.
Wait, so
Just one last thing, sorry. Why is generic state into the D? You have a basis which is just D-dimensional.
And now you have to choose each of your coefficients.
It's very.
Each of your coefficients. C1, C2, C3, volume.
Okay, I'm with you guys. Thank you.
okay,
Yes, yes.
so the upper bound of the complexity is double exponential in the volume of the system in that case, right? Or
Say again.
So yeah, we got it all.
no, I'm asking. No, you're saying it's just exponential in the volume.
So that the number of.
Okay.
Roughly the dimension.
Okay.
The number of steps is.
As you make n steps, volume will factor in.
Okay, so now, so what we want to do, so we phrased our requirement on the states in terms of some upper bound on the complexity. So what we want to do now is just count the number of states in the Hilbert space which have complexity less than or equal to C for some given C. So this also has to be upper bounded by the total number of circuits of length C just by this definition, because maybe by making two different circuits you get to the same state. So this is less than or equal to number of circuits. Actually, can you still read this or should I try to move the board up? It's okay. Okay. Number of circuits with C gates. Okay, and now we can just count the number of such circuits, right? Because so we want to decide where to put our C gates in the circuit. So first we choose which pairs of qubits we want to act with the gates on. So there are and choose two choices for every gate that we have. And then we also have to choose which gate out of our set of G gates we want to act with. So we have to make this choice, and then we do this C times. Yeah. So this gives you some power C. Okay. So good. So then this, and this is essentially just n squared. So this becomes less than or equal to e to the log n squared plus log G times C.
Number of
Mod.
choices per unit.
Okay, but you're making that to be some like.
Whatever.
Yeah, something like that.
Whatever they fix them once and for all.
Yeah. So it doesn't matter. So the important factor here will be just log n squared. And then this is being multiplied, the whole thing is being multiplied by C. I should have just written on that side of the board. Is this clear enough to read or? Okay.
Yeah, obviously, yeah. The policy, which is the number of steps. Right?
Yeah.
Okay, perfect.
Recently that there is a gate, maybe this is common knowledge, commutes. So if you act, I mean, here the way you wrote it is as if things don't commute, right? These gates that you act on two qubits don't commute. That's why you at every step you have this.
Sure. Yeah.
So there exists like one gate, I think.
Okay.
I mean, up to unitary transformation, which commutes. So I was wondering whether that is enough to reach any state. That's probably, tangential, very tangential. We can talk about that.
Okay. Yeah. But probably you mean it commutes with with all the other gates in the. Sorry.
Yeah, I mean, if you just use that, it sequence doesn't.
I see. You can just use one gate instead of using these many, and then. Yeah. In any case, this is just an upper bound, so I'm sure there are better ways of doing it. Okay. So yeah, and then in our setup, so for us,
the number of steps n needed to reach a typical state in the different space exponential and then dimensionality. Not the difference.
No, it's the language.
Is the right, that's what I'm, okay.
Thank you.
yeah, so this is less than or equal to e to the log, or so n was log of L, dimension of L, dimension of R squared. So, okay, so this is less than or equal to, so for our purpose, factors of 2 next to the logs and things like that will not be very important. So I'm just going to write this, or maybe I can keep it for now. So this is less than or equal to e to the 4 log LR times B. So this will be, oh, okay, sorry. So when I said sub-exponential complexity, I meant that I want C to be less than or equal to B to the alpha for any alpha.
The dimensionality of L into little L, little R into capital L into capital R, right?
It should be the log of that because it's the of qubits that I'm modeling the system.
Okay,
with.
log of that.
Yeah.
But then some you do want little L, want little R, and what? Below that for us and little N equals, they're not. Capital L has the same dimensionality as little N, so that square goes up square.
Yeah,
And then capital R,
has the same dimensionality as small r.
oh, is that right? Okay, it's the pairs.
Yep.
Okay.
Yeah, so actually this should just be a 2. Yeah, and the 2 is coming from this n squared. Anyway. Yeah, so now from the restriction that the complexity is less than or equal to b to the alpha for any alpha, I will have that the number of such states will be less than or equal to this for any alpha, which is greater than 0. Okay, yeah, and just one thing to keep in mind, which I mentioned before, is just that the set of states of low complexity is not like the set of states of low energy, which form a subspace. So in principle, I definitely have enough of these that I can form a full basis of the system, and then I can take linear superpositions of them to get to all the states in the system. So it's really a set and not a subspace.
Yeah, that's fine. Can I say the following? So here, the definition of complexity requires you this to have this local structure for the Hilbert space LR, right?
Yeah.
And that in the previous discussion, you did not have any of that. It was just some, you want to talk at the level of just some Hilbert space.
Yeah.
Right?
Yeah.
And from there, you probably can deduce the number of states that you can achieve so that they have that property of approximately preserving inner product.
Mm-hmm.
And here, is it just the observation that if you have such a model,
Yeah.
with that bounding complexity, the number that you get is the same as that number.
Yeah,
And
it's
hence you can
consistent.
say that those are low complexity states.
Yeah, but it won't be exactly the same. Like this is just some upper bound, and in principle, you could add a few more states to it, like order one number, and you would still satisfy. So this is just showing that this is one feasible restriction, which gives you a small enough set of states.
No, but let's say I'm not having all this stuff.
Yeah.
Qubits and so on. From this previous discussion, I could get a bunch of states which are preserved approximately the products, let's say.
Yeah.
For a typical unitary.
Mhm.
Now, is there something inherent about those states that make them low complexity states? Or is it just the matching of this?
I think it's just the matching of the numbers. Yeah.
I think she got just from the total.
Yeah.
But it could be those states like that.
But as you said, you not in that counting of the number, you not put the structure. So then I can choose the structure to make those hypothetical.
No, but you may not, right? Sometimes.
But that's
you
something
may
to be able to. And given any one state, I can always make it hypothetical.
No, but let's say from the previous discussion, the states that make it work are some special set, special type.
I think you just need to compound on the number of.
Yeah. That's the only thing that we end up using because our
There's some distribution also, right, on the sphere. They probably are distributed. You cannot pack them up in some cone, for example, with some small angles, even though those are small, right? So you are using some kind of distribution of those sets, and the state that would come from this kind of high complexity states are probably also of those types.
Can't I choose, given any state, can't I always choose a Gram-Schmidt basis to make it 1 0 0?
No, but not any state, right? You have to work with, you simultaneously work with all those states.
No, but at least for one.
Yeah,
One I could certainly make it hypothetical. You're asking, could I make 2 of them?
no, all of them.
High,
Sorry, Low complexity, low
No, but I'm
complexity,
saying I can always make one item. Nobody can solve it.
yes.
So it can't be that I can prove that all of them will be low.
No, but it can be made into low.
Alright, by an appropriate choice.
Yeah.
Okay.
That there exists some sort of a local arrangement of systems, so that all those states can be thought of as low complexity. That is a non-real thing to say, right?
Yeah, I think not just with high probability, but
Yeah, I'm not sure that our model has enough structure to. Like, I think that at this level with the random unitary, you just end up using the number, but maybe you can make a different model where you actually use some special structure of the states. But I think from everything that I said so far, we will just end up using the number. Yeah, so the main thing that we end up using in the rest of the discussion is just that the number of states of sub-exponential complexity is upper bounded by this.
So I understood, of course, into that formula, less than equal to, when if you wrote down, if you put your little n and you input your
C.
C, which is e to the alpha, you get this now. Right?
Yeah.
But then what was the sub-complexity, sub-exponential?
Yeah, sub-exponential just refers to this constraint on the
Okay,
complexity.
yeah.
Yeah.
because
E to the, so.
because C equals B would have been maximum.
Yeah.
Because that would have gone.
Well, actually, C, yeah, but it would have been exponential in LR and not B. Sorry, in the size of L and R and not B. So the parameter that we want to use here is really the black hole entropy and not the naive size of the system.
Yeah, that's why is sub-exponential? The maximum was not, that's where.
No, but she's saying maximum 90 would have been on L.
Yeah.
Because she was working this other space.
Yes. And somehow that is related to.
B is smaller than that, so she wants it to be even smaller than that.
Yeah. Yeah, I could have taken it to be sub-exponential in the dimensions of, sorry, I could have taken it to be the statement with B replaced with LR, but which would also have been smaller than the generic number of states in the system. But somehow it seems that things work much like to get things to actually work, you need this restriction and not the weaker one.
And alpha here will be less than 1.
Alpha, yeah, no, for any alpha greater than 0.
This is because actually the underlying system has functionality much bigger because of little L and little R.
No, but I want this to be true for any alpha greater than 0, including 1, but also if it was 1/2 or something. I just want it to be something like, yeah, like it can't be anything which is exponential in SPH, even with some. Yeah, so if I say that.
The more things. That,
Yeah, I'm just saying that it has to be, it can't be of the form e to the alpha SBH for any alpha.
I thought, let me make sure, isn't more the dimension of the e to the SP?
Yeah, exactly. So this is less than this for any alpha.
For any alpha.
Yeah.
Oh, so not that there exists an alpha. It
Yeah.
would be less than this for any alpha.
But including.
So I want it to look something like a polynomial in SPH. Yeah, exactly.
Yeah, one thing I understand actually, but I mean, just to get it right, it's possible in your setup to have had states with even complexity greater than the SP, right?
No, she's saying it has to be true for any alpha. So not just for large alpha, not just for alpha greater than 1, even for alpha equal 0.000.
Yes.
It must be very slow.
So for now, this is
Yeah, but you're
not
saying in
about-
principle, I could have had states here which could have had complexity higher than e to the SPH. Yeah, that's true.
Where you require enough steps to get to, I guess.
But here, yeah, but this is a strong restriction of size.
Sorry, so what exactly is about? I mean, you say if you have some number of steps.
Yeah.
And.
Well, this is just an observation for now, right?
This is just
If you
a,
want
yeah,
it to be bounded by this, the number, and then you will tie it to the
yeah, that's it. So yeah, this is what I've derived so far, but I can tied it to the previous discussion. So,
The statement about number of cubes.
yeah, so now I'm going to make a statement about measure concentration, which combined with this will be helpful for us. So, yeah. Okay, so yeah, okay, so for this, I will need some definitions. Okay, so I'm going to use, so in general, measure concentration is a set of statements which tells me that if I have a probability distribution on some high dimensional Riemannian manifold, and I have reasonably well-behaved functions on it, then the probability that they deviate from their average tends to be very small. Okay, so for this, we should define what we mean. So the manifold that we'll be interested in for our setup will be the set of d-dimensional unitary matrices. And
Continuous version of the ball plan.
yeah. Exactly. Yeah, it'll be something along the lines of the law of large numbers, which is also bound on the probability of deviation from the average. Yeah. So the group that we'll be interested in will be UD, and we'll consider some, like, the quantities that we've been looking at are some functions from UD to the real numbers. Yeah, so we'll say that kappa Lipschitz function f from UD to R is one for which you have some continuity property, which is that f of U1 minus f of U2 is, or this is just an absolute value, is less than or equal to kappa times U1 minus U2 in the L2 norm. So this is some measure of the distance between unitaries. And we're saying that the distance between the values of the function is upper bounded by some constant times the distance between the unitaries. Okay, and
Unitaries to R.
yeah.
Defined in some way.
The only restriction we're putting on it is that it has this Lipschitz continuity property.
And the L2 norm is the standard L2.
Yeah. So let me just write it explicitly. So this means square root of trace U dagger U. Okay, so then we use the following measure concentration theorem that for kappa Lipschitz function f in the Haar measure on UD, the probability that f minus the average of f over the unitary group is greater than or equal to epsilon will be less than or equal to 2 times e to the minus d epsilon squared over 12 kappa squared. Okay, so this is just something which is telling me that for large epsilon, this thing goes down and it's suppressed in the dimension of the unitary group. So if you have a sufficiently large Hilbert space, then this can be small. And you also want kappa to be something sufficiently small such that this bound is useful. Kappa is the thing which appears in this Lipschitz continuity of F. So this is the probability that
Okay.
the difference between F and its average is bigger than epsilon. Okay. Yeah, so maybe I'll explain, I can try to explain more about how we apply this to our setup. There are a few more kind of technical steps in actually applying this to the quantity that we were interested in, which was the inner product. Before, yeah.
Just one question about it. So, Stafford-Lefschetz function says that they should grow or whatever, they should change in a, with some slope, right?
Yeah, it's telling you that F is not, is like a reasonably well-behaved function. Or something. Yeah.
But now if I just keep on doing that, why can't I get some, is it because of the compactness? Bound is because of the compactness of the group? Because I cannot go like that, I have to come back. But I can still do that wave. Okay, then, no, but then I still seem to, I don't seem to get that, probability meaning in the space of all. Sorry, what is this probability?
The probability is over different choices of U. So F is a function of U.
Okay, now I understand.
And this average refers to the average over U of F of U.
So the probability that acting on any U, F returns a value bigger than its average,
Mhm.
that probability that is greater than or equal to epsilon, is that what you're saying?
Yeah.
That is bounded in this.
Seems like you have, I mean, the naive, let's say circle, in the circular case, for example, you could have a wave. Right? As long as its sign is bounded by some number, not very jagged wave. Then you seem to get, reasonable chunks of the circle where F deviates from its average, right? So we this the function F. Yeah. That's a wave on the circle. Yeah. And it's not very jagged in that it respects that kappa. Then still there is a chunk near the peaks of those waves. Where the
Yeah, but sorry, but yeah, but in that case, D is just equal to 1. So you don't get a very strong bound in that case. So for this to be useful, you really want D to be large.
this computation doesn't work for that.
Yeah, exactly. For the case for where you have a large dimension is the concentration really comes from the large dimension. So yeah, the more intuitive case is like if you consider functions on SD.
Yeah.
Then for the d-dimensional sphere, as you increase D, you can see that most of the volume is just concentrated around the equator. And so if you have a function which is not varying in a very crazy way, then its value typically will be pretty close to the value at the equator. Yeah, but yeah, it's good to notice that it doesn't work for low dimensional cases.
Yeah, I'm not understanding the left hand side. So the probability that capital F, just capital F gives a value different from the average. And what's the mod and O? That's greater than equal to greater than equal to epsilon. That symbol giving the bracket.
Yeah.
Got it. That's right. Excellent. Thank you. Okay, so this is some statement regardless of what K is.
Yeah.
Okay, go ahead.
Okay. Okay. So in actually applying this to the function we're interested in, which was this psi tilde in a product with psi tilde, that will require a few more steps. But let me tell you what result you get from doing that. So we'll find that the probability psi 1 tilde, psi 2 tilde minus psi 1, psi 2, which was the average of psi 1 tilde, psi 2 tilde, is greater than or equal to b to the minus gamma is less than or equal to e to the minus b the 1 minus 2 gamma for any gamma which is between 0 and 1/2. Okay, so you get this by choosing f appropriately, and then by choosing like then for that choice of f you'll get some kappa, and then you can combine the different basically when you do that, then the way to get both this error epsilon and the quantity on the right hand side to be small will end up being to take epsilon to be b to the minus gamma for this range of gamma. And then on the right hand side, you get something which is also small.
So now, just to understand, because you didn't go from psi1 psi2 psi1 tilde psi2 tilde to some unitary, but unitary plus projection, right? I mean, how are you
Yeah. Well,
using this result there
yeah.
By saying that you're starting with a unitary and then with a projection, but anyway you import it as something. Is that the point?
Yeah, but eventually, whatever I did, this thing was also a function of the unitary u.
Was the function.
Yeah,
And that function is a Lipschitz compound function.
yeah, exactly. So actually, the thing that I end up using, so it will not be like if I directly use this as my f, then I get a Lipschitz constant which is too big somehow. So I have to go through a series of indirect steps which are a bit technical, but the correct f to use ends up being just the norm of the state after I apply my map. So yeah, so maybe I can briefly mention.
I mean, just saying, I mean, just
Yeah.
roughly you've taken that original unitary and win some function out of it.
Yeah.
But it is just that that function is corresponding to the inner product, is it?
Yeah, that function, yeah, I choose the function to be something like this inner product.
You can do that.
Yeah, then I can do that as long as I can find a small enough kappa for it. Then I can just put that into this expression.
This is just saying it's like a normal distribution. Your
Yeah.
standard deviation was 1/2.
Mhm.
And then if you've got like an x deviation after that, it should be like e to the power minus x squared by.
Yeah.
And now you put x equals that e to b to the power minus gamma, and you get that, right?
Yeah, exactly.
Technically what it is.
Yeah, but somehow in getting these steps, this factor of d was pretty important.
Yeah, you have to use the law of large numbers.
Yeah.
To get it, so that all distributions are normal. That's what it is. Right?
Mhm, mhm. Yeah, sorry. So from what we said before, this psi1, psi2 is also the average of this quantity.
The reason one that half appears there is because that thing squared was 1/2. But I hope I got that right. That expect that psi tilde psi minus average, the whole thing squared,
Mhm.
that was 1/2.
Yeah.
Right? So that half there is squaring to 1/2. That's why things only work for that. If you want some deviation to be larger than the standard deviation,
Mhm.
then it'll be described by the law.
Yeah, and why is it 1 minus 2 alpha?
You see, write it as e to the power minus x squared by standard deviation squared.
Yeah.
So standard deviation squared was that b.
Okay, so that's the one.
Yeah.
Yeah.
Standard deviation squared is 1/b. Yeah, and then the.
Thank you so much.
And the x squared was that e to the b to the power minus 6.
Okay, so yeah, so now once we have this statement, how do we apply it? We now want to consider the probability that if I consider the maximum deviation for the set for all psi1 and psi2, belonging to this set sub X. So if I want this maximum to also be, yeah, so basically this is the probability that any of these things will be bigger than b to the minus gamma. Then I can just use the union bound for this, and then I get a factor which looks like e to the sorry, I'm just saying that the probability that it's just the probability that any of these is bigger than this. For this, I can just add the individual probabilities.
The actual probability might be less than that.
Yeah, but this is just some upper bound. Yeah. I take that number and square it, right? So this just is like n sub x squared.
Like what you're going to write the right hand side from that right hand side. Then that will be equal to that.
Which right hand side, sorry?
I mean, what you're writing there will follow from previous line, right?
Yeah, exactly. So now I just multiply this by the number of all possible pairs.
By all possible.
All possible pairs psi 1 and psi 2, which are drawn from that set. So then I just get n squared times what I have on the previous line.
So this is really a result. Then all the complexity is words out.
Yeah, the complexity is a way of getting this to be small.
But
Yeah.
this is the
Yeah, so then if I do it, if I just write out both of those factors, then it looks like e to the log LR times b to the alpha minus b to the 1 minus 2 gamma. And recall that this was for any alpha greater than 0. And for any 0 less than gamma less than 1/2. Okay, so yeah, so I can choose alpha and gamma such that this thing is always such that this term is bigger. And so then I have some suppression, which is of order e to the minus e to the SPH.
But it's not like this complexity thing is exactly maximizing.
Yeah.
The function you're getting here is just the square root of that. N squared times that has to be equal to 1.
Sorry.
So that's a different analytic form from this law. I mean, this is one way
well,
achieving.
The log, yeah. So in doing all this, I'm also assuming that log LR is not something which looks like b to the alpha. So I'm assuming that LR is not doubly exponentially large in b, which is where the assumption comes in that I'm not at extremely late times in the elaboration process.
Okay, yeah.
Yeah.
I'm saying there's no clean, it's not a very clean fit between the formula you get from complexity and the formula you get from your number. One saturates the other, but it's not like you get the same formula.
Can you just even explain that remark? Sorry. So just so I understand the chain, now you just say, look, suppose I had n independent these objects. Then this is the amount I would get. So that much I understand. Why did it become n squared? That's the number you're taking?
Oh, that's just because I'm taking pairs. Yeah.
Pairs.
Yeah.
That makes it n squared. Okay, I'm with you. So that is the number of pairs. Okay. And now I thought you were going to say how big can n be so that this probability
is less than some tolerance.
Yeah. So this
So that will be like square root of your 1 over square root of your whatever thing.
that bracket.
Yeah, what you're counting. Yeah, that's not going to log LR.
yeah, I will eventually want this number to be something which is not exponentially large in b. And one way of getting that is to
Right, I mean, the logic should, something says you should just make that number less than some
some
your tolerance,
tolerance,
whatever.
and then figure out what n should be, and then match that n with that. The one that you have from above.
But it doesn't quite match, right?
Yeah, it doesn't quite match.
That's why it is
Very, very.
It doesn't match at all. I mean, what I'm trying to ask is, sorry, just let me ask you dumbly.
Mhm.
If I just put n sub exponential square and that bracket, I thought is e to the minus mod b one minus theta,
Yeah, that's right.
right? And I say that this is less than, okay, epsilon.
I think she wants it to be less than e to the power minus something b. You want, what is your tolerance?
I want this to be something which is, yeah, like unless this is, yeah, if I get something here which is exponentially large in B, yeah, I guess what I can fit here, because gamma has to be between 0 and 1/2, it seems like I could in principle have had something which looked like e to the b to the 1/2 minus epsilon or something like this. But instead, yeah, but what the set of states of low complexity gives me is something which is less than this for any choice of alpha. So yeah, you're right that it is smaller.
So you can, physically, not orthogonality would not have the tolerance physically would impose certainly not e to the minus. I mean, that's like some absurd tolerance. I'm a physicist, I'm going to do measurements, it's going to be log of, it's going to be m Planck or something in the denominator compared to analysis. So I wouldn't have put the tolerance epsilon as scaling like e to the b or something, but just some fixed number.
If you do that, then you can get away with very.
And then you just let me understand that, maybe that's wrong, but then I would have got n sub exponential to be something like e to the mod b, 1 minus 2 gamma over 2.
Yeah.
Okay, and that, now just to understand the chain of logic,
Mhm.
I'm going to compare that number with what? Yeah, sorry, I got lost. But to compare that number with.
States there.
Sorry, this,
I think, I would say at that stage that you finished. This is the number of states in your set that you're allowed to deal with. If you deal with more, you'll be fine. Now they are forcing the notion of complexity. I mean, not in a very clear.
Okay, then I would have said, if that's the case, sorry, just to understand, that the number of states you can deal with is, as you said, gamma.
gamma is just any number between 0 and 1/2. So in particular, you could choose it to be just a little bit smaller than 1/2 or something. Or you could choose this number to be.
But actually, you can, I mean, with the tolerance, which is with inner products which differ by, no, my point is, how are you doing the physical thing? That is, I mean, can I take with,
Yeah, so gamma is appearing here.
eventually you were trying to ask that you have a map into the side one side into your tildes were just maybe it's.
The tildes just referred to acting on psi1 and psi2 with you, with this.
Was the map into H
Yeah, exactly. Yeah.
and you want approximate. Okay, so let's say you can't get away, I guess you can only get away with gamma of about half or so. No, or less than. Huh? Okay, so roughly that is telling you something about that. And the number. I guess, sorry to be sort of, where you were going with this was that you would have a number of states which are approximately orthogonal, which is the number of black holes. That's where we were going, or no?
Number of states inside the black hole where you won't see deviation from it.
We won't see deviation, we will order the black hole dimension. That's where we were going. Huh? Is that where we were going?
It's less than W exponential in the black hole dimension because we want it to be less than this.
So if I don't, so if I was just trying to work it out, trying to look at use the first line of your inequality.
Okay,
Then what would I get for n? I think I would get n is roughly to the mean.
with some small exponent, yeah.
Yes. No, but why is that, sorry, I don't know, why is the a priori expected, there's some a priori expectation about the number of things.
So I think it's something that is saying the following. In my physical picture of this track, these are the kind of states you can get in ADS CST by time of boundary time of it already zero. Right? So if you have time of reading about the ETS, you can get to the ETS. I think that's how I see. So from boundary point of view, because those are fundamental, those are like the states you want to be in your system in your purpose.
And this is little smaller than the S, because this, yeah.
But
Little,
yeah, but if you said gamma equals half, I think you could also have done this with, anyway, we get chocolates.
I mean, I guess her point is, okay, at least one point is that you want to put in some cost in. If you don't want them to deviate too much, so gamma is little above.
But you could have done the cost as 1 by b times x, where x is a number. These are going to be large compared to standard deviation. After that, it doesn't have to be parametric in that one. I don't think it should just be 1 by b times x. If x is a large number, all of this.
So then basically you say the number of states. Then the number of states, if the gamma is, sorry, Shreya, so you are gonna take gamma to be what again?
See, in that probability function there,
Yes.
let's take that 1 by x squared to be times x, where x is any large.
Yes, times x.
Okay, x has to be large compared to 1, nothing more. Then I think your probability will be e to the power minus x squared, e to the power minus bx.
Yeah.
Because that's just the normal distribution. Okay, and now we can do it with that. So we're going to set some tolerance. So
Your probability is this is greater than g to the power minus x square.
yeah, I want that this deviation, this actual inner product minus average inner product is greater than x divided by square root.
X divided by square.
I'm choosing square root because square root is the expectation of standard. Yeah. Okay, I just want this to be large. X to be large. She made it large by making x. So then you will get e to the power minus x squared minus b times x squared. And now it's a matter of how tolerant you are. Your x is your measure of your tolerance. And you will get it this way, and that will be exactly the same.
E to the minus 6.
Well, e to the power minus bx.
So you want to take, don't you want
The standard deviation was 1 over.
1 over b? So you want to take the number to be x over b or
X over square root, because this isn't the square root. So it's not in the square. The deviation was of this quantity square.
No. So you can basically, instead of requiring this to be suppressed relative to this, you could also just have said that this is some small number,
Yeah, and see,
which with the same dependence on B.
in your first line, then the probability, we could have made a requirement that it's greater than x divided by square root. You know, okay? That would anyway be some sort of exception when x is large. Because the average measure of these fluctuations are 1 over. And then we can go through this whole thing and we'll get exactly that.
So, but, I mean, just to say, if you had some variance and you were some multiples away from the square root of the variance, then what the probability of that is there's that multiple, it could have been e to the minus x squared. You know, if I normalize, I don't know.
Yeah, you got it.
I don't know.
It would be minus x.
Yeah, it would have been e to the minus x.
Now you choose that probability, now you multiply that probability by the number of hints
Correct, to get one.
to get one, and
So there's no factor mod.
oh, then it. Yeah, there's
So
no.
no factor mod b, then the number would have been this. I'm just saying, if that's what we are doing,
Yeah.
Yeah, you need that little bit of gamma to get a little bit of beta.
Right, you're right, I said it wrong, sorry.
No, I mean, your basic point, I understand.
Yeah, because gamma equal to half that goes away, right? That factor goes away.
But, okay, but what are we trying to get at? I mean, just to, sorry, Shreya, just to
Mhm,
understand.
mhm, mhm.
I understand, I mean, we're trying to say that the, okay, we had this map from a bigger Hilbert space, non-isometric map. Bigger Hilbert space to this blackboard Hilbert space.
Mhm.
What you were trying to get at, what? About the entropy of the black hole or e to the one of the two is I.
Would have said that it should be something that is s- less than e to the some number of states, which is less than e to the entropy.
Entropy. And just to go back to perhaps what John was saying, I understand, would a chain to get to that could have just been the map you set up involved a unitary. For things involving unit functions on unitaries, I have the Lifshitz K bound. So that I'm not introducing notions of complexity to circuits. I have the K Lifshitz bound. What you have is a map involving unitaries. After some clever things, I adapt the Lifshitz function result to that map and obtain a bound.
Mhm. And then that be some restriction on what this number has to be, which is much smaller than the full number of states on the semi-classical Hilbert space. But yeah, and then one way of satisfying the condition on that number is to restrict to the set of states of low complexity. But I agree that the actual number could be bigger than the set of states of low complexity and still satisfy this condition.
In particular, it could be like some small set of high complexity.
Yeah, it could include some set of high complexity states. That's right. But if you wanted to give some physical restriction on your Hilbert space that can justify putting a limit on this number, then it seems like one way to do that is in terms of complexity. I guess your argument is also implicitly using complexity because you're saying you can't generate arbitrarily. Yeah, but
I'm using the fact that you want to generate these states in the bulk as semi-classical states using boundary diagonally.
Mhm.
Boundary diagonally you can only get with.
Okay, yeah, that seems reasonable.
And it's really many times, sorry, go ahead. No, I'm just gonna just confirm that it's really not clear that the set picked out by low complexity criteria and the set of states picked out by this criteria are identical or.
No, it's not clear.
That's not.
It's not clear. In fact, it is smaller as we just pointed out. So
Yes.
yeah, that's right.
No, I mean, in terms of more detailed distribution. I mean, even if the number had matched,
Yeah,
you would have still left with this question, right? Whether it is the same set.
yeah, that's right.
You are
Because
providing
yeah.
Some confidence.
Shreya, at very late times,
Mhm.
log LR will keep growing. So at some stage,
Yeah,
there'll be a process.
yeah, that's true. So yeah, for that range of times, we don't have anything to we expect that this whole description, you need something more at those times, which is not captured by this. But that's right. So so we'll be restricting to a time such that LR is not doubly exponentially large in B.
Take some X, like, if you're ready to say that. So I'm just saying that B to physically, that instead of that B to the minus gamma, we will just pick some. And then what you would have got is e to the minus d because of the black hole dimension times some. So I think what I'm trying to say is that, physically, I may not have put b to the minus gamma. I might have just said I'm willing to live with approximating psi1, psi2 up to some tolerance It doesn't have to scale like the black hole Hilbert space. And if I'm willing to do that, just for a moment, suppose I replace, let's use the variable x here. Probability for support greater than equal to, instead of b to the minus gamma, some x, fixed sum.
Okay,
Then you get dx.
Then you get,
It's a parameter.
then you get e
Yeah.
to the minus, you get e to the minus b with that x. Right?
That's right.
Yeah.
And then therefore the number of states would have been e to the b.
Yes, that's a good way.
And that is physically what you're after. Yeah, you get only a number of states, which is the b. And it makes a lot of sense.
Absolute units of
Tolerance
not in
should be
units of one.
right, right. Which is actually the correct thing.
And that exactly that reproducible.
Yeah.
You should say 10 gamma to 0.
Yeah. It's
Mhm,
like some
mhm.
absolute right, which is the correct thing to do. I mean, physically, that is the correct thing. Okay, now I feel much better. Sorry. I see. Okay, I understand. And it's basically the B factor here. That, once you have the black hole, you're mapping to the black hole's Hilbert space with dimensionality. That B is going to appear in this. Okay, now.
No,
Thank
but,
you very
but,
much. Sorry.
but in the previous discussion you had when you were discussing these approximate isometries.
Yeah.
One more B was very natural in controlling its.
that's true. Yeah, yeah.
So what was that for? I mean, if you want to do the order one number. Right.
No, it's because one over b controls the deviation. Then something puts an order one tolerance. That's why it gets e to the power minus b. Right. Same thing.
Right.
Yeah, so I don't know. Yeah, I mean, this is kind of subjective whether you want the deviation to be exponentially small or not,
Yeah.
but yeah. Okay, so I can try to say a little bit about operator reconstruction, or yeah,
How
it
long
is.
it takes us to digest even the facts of not complexity, but very simple.
The one comment is that Shreya is also here next week. So if you have sufficient material, then we can also have another like follow-up sector on Monday or.
I'm happy either way, whatever people prefer, because I don't.
You have the energy, Shreya.
Yeah, I'd be happy to discuss more either now or next week. So whatever.
I think that is a good idea.
Next week.
Because it's one o'clock.
No,
Also, we were thinking of, so if you were thinking of taking Shreya to lunch, with Flamboyante, so any please.
If you are okay.
Yeah, absolutely. Yeah, sounds great. Thank you.
let's give her a